Everybody. All right, so right now we are going to start talking about a completely new topic in our course, right? It's going to be a shift in paradigm. We're going to start talking about how to think about building our little programs, our sketches, slightly differently, right? And so I think as a paradigmatic shift and like as a complete sort of like change in approach and thinking about this, um, it introduces a certain amount of complexity, right? So before we even get into this complexity, I want to address why we even need this, right? Like, why complicate things um, if things are working just fine without it? Well, it depends on what you're trying to do. And if there are certain things that, if you're trying to do those things, things are not actually working very well, right? So we can start by looking at a familiar example. We can start by looking at our bouncing ball, right? So like we had this little sketch of a little circle bouncing around, okay? And then we're going to try to complicate this a little bit, right? Like try to enhance the experience, trying to enhance the animation, add some interactivity, and so on and so forth. And uh, and then we'll see where the problem arises and how we can deal with this problem by completely changing the way we think about the entire structure of our program. Okay, so right, so let's start where we started, right? So we have a canvas. Let's make it 800 by 600, the way we're used to, right? But again, the size doesn't really matter all that much. So we have our setup and the draw function. And so before, what we used to do, we used to create a position and a velocity variable, right? So let position x, right? And then that will be, let's start with 0, or we can just declare it without having any value. Let position y, let velocity x, and let velocity y, right? So we have four values that will describe the movement of our circle. And then we can also introduce something like um, radius, right? And let's make this 50, right? So when we create our circle, we'll set the diameter of the circle from its radius, which is just doubling it, right? And we can easily change it by changing the value at the top. Okay, so once we've created our canvas, we can start setting up our positions and our velocities. So should be a familiar thing, but why not go over it again, right? So position X will set up to be width times 0, 0.5, right? And then position Y will set to be height times 0.5, right? So just put this in the center, and then velocity. I believe we used randomness, and so we said random, and then we can set the range. And if you remember, the direction of the movement is determined by whether it's a positive or a negative value, right? So -2, for example, will move it 2 pixels to the left. +2, +2 will move it on the other hand to the right. And that has to do with how the graphic system is set up, right? So we're gonna maybe like do something like between -4 and 4, and the similar thing for velocity y. We'll set it to be random between -4 and 4. Okay, so that should be it. Um, we have a background, and then we say like, all right, so first let's move the circle, right? So we're gonna say um, position x plus equals, if you remember, it's a shorthand for itself plus something, right? Plus equals, so just take the value and add something to it. Velocity x and position y plus equals velocity y. Okay, so we can, again, the order of operations doesn't matter. Like maybe you move it first and then you draw it, or maybe you draw it first and then you move it for the next frame. The frames are going to go so fast that it's going to make very little difference, right? It's almost going to be just an instantaneous flashes for all this code. And then we can say like, right, we can draw this, right? We can create a circle. So we can do like, I don't know, fill of some color. Um, I don't know. Let's just make it black. Or let's make it red. Why not? 255.00. Maybe like a little lighter, like 100. 100. Okay. So it's going to be red. And then the last thing that we did, we kind of like accounted for the bouncing from the edges of our sketch, of our field, if you will, right? And so we said like if, and again, please feel free to rewatch the video where I went into the details of like why and how this is happening, right? But we said that if the position, so let's start with the left to right, the horizontal axis. If the position x plus radius, right, is greater or equal to width, or position x minus radius is less or equal to 0, right? So that means that if we, counting from the center of the circle, right, adding the radius either to one side or to the other side, right, if we are adding it to on the positive side and it's touching or exceeding the width, or if we are subtracting it, so like adding it to the negative side, and then it's touching or going below 0, right, we're just going to flip the direction of movement. So velocity x times equals -1. So we're going to take velocity x and multiply it by -1, which will just flip the uh, sign, polarity, if you will, of our value to the opposite. So if it was minus, it will become plus. If it was plus, it will become minus. Right, and we're going to do the same thing for if position y plus radius is greater or equal to height, or position y minus radius is less or equal to 0, we are gonna say that velocity y times equals -1. Okay, same deal, right? So we can just double check. Let's see, maybe we have some errors. I don't know. I haven't checked it yet. Oh yeah, we never drew it. That's fantastic. So we set the color, but we never drew the circle, right? So let's do the circle, and then we'll say position x, position y, and then radius times 2. Okay, so that should hopefully take care of it. All right, so we have a red circle that's just kind of like nicely bouncing off of things. That's great. That's all fantastic. But let's say we have several of those, and we want several of those. And so if you have several of those, obviously you will declare those values as arrays. That's one way of doing this. You can say position x would be an array, and then position y would be an array, right? And velocity will be an array, and so on and so forth, right? So you declare them as arrays, and then you fill in, like, you just start pushing values and then adding stuff to arrays. So like you would say, instead of position x equals, right, you would say like position x dot push, right, and then this value, right, and that would be the first value in the array, so index 0, right, and then we start going from there. So you have to maintain 4 different arrays, and by the way, the radiuses will also be arrays. So I'm going to have an array with the value 50 in it, and then I'll add some more values every time I need to add another one, right? So if I have 10 circles on the screen, I'm going to have to maintain at the very least 5 arrays of each of 10 values. And if I also want to have them in different colors, I want to add another array where I will keep track on each and every one of their colors, right? And God forbid one of the arrays gets untangled, right? And like maybe one will start having 9 values and the other one will have 11 values through some weird error, right? Like programs get complicated and errors creep in, right? So the simpler you can get here, the better, right? So maintaining this many arrays, all separate, is like it's just a cognitive overload. Maybe not for computers. For computers, they don't really care, but for us, right? When we're writing our code, we're trying to express ourselves first and foremost, right? Um, and so for when you're trying to understand what another person wrote in code, it's also helpful to try and understand how they try to express themselves. So in order for us to kind of deal with this weird complexity, right? Which, by the way, is further complicated if I wanted to start adding those circles, right? Our little bouncy balls on the fly, right? What if I want to like have clicks and every time I click, a new one appears? So I have to go through this operation of adding a whole bunch of new values to all of the arrays that I have. And if I have, again, a more complicated system, I might forget something in one piece of like add something in one part of the code but not in another, or have those values get disentangled and so on and so forth. So this is an issue, and it's just a complexity that we can deal with. But if only we change the way we think about things a little bit, and we allow ourselves to be expressed in this new changed way, things become simpler, right? And this different way, different approach to programming is called object oriented programming. So, the reason why it's called object oriented programming is that we stop thinking about our bouncy balls as a collection of arrays, right? Like you stop thinking as a collection of separate values, right? So I have position x, position y, velocity x, velocity y, and just like they're just values in the ether floating around. And yet somehow they create a thing on the screen, and that thing is a thing on its own, right? Like it's kind of like it's in its own enclosed system, right? And so this is what object-oriented programming is. We start thinking about our code not as just like weird disparate collections of values, but we start saying like, all right, I have a thing, right? Let's say it's this bouncy ball on the screen, and that thing has certain properties, and it right, so like it possesses certain characteristics, and it can do things, right? Um, it can perform certain actions, right? So this is where object oriented programming starts. Okay, so let's look at an example first in a schematic way on a diagram, right? We're gonna look at an example, and then we're gonna see how that example can be used in order to implement it in our system. Okay, so an example that I have is an example of a pond, right? So imagine we're trying to program a simple system that is supposed to represent a pond with some, usual suspects that you would find in a pond, right? So I have a lotus, right? It's a thing that grows in ponds, oftentimes. I have flies, they tend to buzz around, right? And then I have amphibians. And the reason why I'm calling it an amphibian, right? Let me zoom in a little bit. And the reason why I'm calling it an amphibian is because it's technically a frog, but when frogs start their lifetime, they're called tadpoles, right? So, and then at some point when they grow legs and arms, they become frogs. So, amphibian is more generic way for saying it's something that starts as a tadpole and then becomes a frog. Okay, so all right, let's look at this system and its components, right? So again, we said that like if we're trying to program it's good for us to have like a decent abstraction, right? And so I'm using something called a UML diagram. UML stands for Universal Modeling Language, and it's a way for you to just kind of like model things in your system. Okay, so we have a lotus, we have a fly, and we have an amphibian, and we have a pond, and the pond sort of like is a place where these things happen and they interact with each other, right? So amphibians have properties, right? Like they have certain characteristics, and they can be expressed in values or numbers or like just various kinds of various kinds of data, and then they can do certain things, right? So, for example, let's go through the characteristics of an amphibian real quick. So, um, so we can start by asking, is it a tadpole? Yes or no, right? So that's probably something that's going to be tied to its age, right? So let's say like for however many frames, right? Like however we want to encode their age, let's say for the first 2000 frames, we're going to consider it a tadpole, right? So that's going to be yes for this question, right? And then after the certain age passes, then the tadpole becomes a frog, right? Maybe changes some visual characteristics. You can start plumping, um, again, legs and arms and so on and so forth. So is it a tadpole or not? It's sex, right? Its age, its size, right? Maybe like as like things tend to grow, living things tend to grow, and so we can encode the size as a value. What's the color, right? We can have a somewhat differently colored. An important thing to track for a living thing is whether it's actually still alive or not, right? Like it's born, and then it's alive for a little while, and then it's not alive for the rest of the rest of the time, right? And then we can measure its hunger, let's say on a scale between a 0 and -10. The lower the number, the more hungry it is, right? The less nutrition it has in the system, or whatever, however you want to represent this, right? So those are all going to be characteristics of amphibian. And what those characteristics are depends entirely on you, right? It's a creative enterprise. You're trying to build a model, right? A simulation of a pond. Maybe it's a game, maybe it's an interactive experience, maybe it's an art piece, whatever we would want it to be. And so how you encode those, which characteristics you choose, is going to depend on how complex you want your system to be and what is it that's important for you, right? So maybe there are certain characteristics that I am not encoding here. So for example, um, frogs have eyes, right? And maybe we can track how good its vision is, right? Maybe like just like with people, and not a biologist here. So bear with me. Maybe frogs have different, like some of them have 20/20 vision, and some of them have not quite such a perfect vision. And so we could track that if it's important for us. Maybe it is, maybe it isn't. I am not tracking it in my model. You could track it in yours. It's up to you. Okay. And then we have certain things that an amphibian, our frog slash tadpole, can do, right? So it can ribbit once it becomes a frog, right? So that may be something contingent on whether it's a tadpole or not. If it's a tadpole, it cannot ribbit. And if it's a frog, it can start ribbiting. Okay. It can swim, it can eat, it can sleep, right? It can breathe, it can procreate, it can leap. Again, something that might be contingent on it being a tadpole or a frog. It can poop, right? So like it has a metabolism of some sort. And just like with the characteristics, right? There are certain things that I might be tracking, I might not be tracking, right? Um, so I am fully in charge of the list of these, both properties, which is the characteristics of it, and also the things that it can do, which technical term for it is methods, right? So method is an action that your object can perform. Okay. So we have amphibians, we have flies, right? And just like amphibians, flies have characteristics, age, sex, type, whether it's a larva or not, whether it's alive or not, its speed and flight, its altitude, its hunger and size, and so on and so forth, right? Flies can fly, they can bite, they can rub hens, they can poop, drink, eat, whatever. Maybe you also want to add procreation there, maybe it's not important for you. Entirely up to you, right? Similar with lotuses. Lotuses tend not to move around a bit. So you might have size, color, whether it's flowering or not at any given point. Its age, location in a pond. Again, like since it's not moving around, maybe location is something that you would track, alive or not. And then lotuses might photosynthesize, might grow and float, or maybe you will track some other properties of it as well. But the important thing is that all the objects in your system possess properties, right? Certain characteristics of what that tell us who they are. And they can do certain things, right? They possess methods. And another component of this paradigm is that they can have relationships. They can exchange information. So, for example, an amphibian can eat, and when it eats, right there, right, like you can see, yes, I can eat. And what does it eat? An amphibian eats a fly, right? So, like, if an amphibian eats a fly, then the fly stops being alive and the amphibian starts being less hungry, right? So they can exchange certain, they can interact, like, right, like as components, they can interact and they can exchange certain amount of data. So maybe I can say, like, if the size of the fly was really big, right? So then the amphibian that ate it, let's say like 10 pixels, right? And if amphibian ate it, its hunger um, was reduced by 10. And if it was a small fly, right, like a tiny little one, its hunger was only reduced by 5, right, according to its size. So they can interact and they can exchange information and they can exchange data. So same, like flies can sit on lotuses. So if the fly stops flying, then its location might be tied to a location of a lotus, right? And so that's something that that's the information that's going to be passed on from the lotus location to a fly location, right? And so further on, you can have like interactions between amphibians and ponds, lotuses and ponds, flies and ponds, and so on and so on and so forth. Depends on how complex you want your system to be, right? This is a fairly simple representation, okay? So we can create a system like this ourselves. And in order to do this, right, whether we are doing it um, from like whether we're doing it in a diagram like this or whether we're going to start doing it in code right away, we need to create a sort of an idealized blueprint, right? So here I have sort of like a diagram of an amphibian, right? And from that blueprint, I can birth however many amphibians I want or flies, right? Like I can have swarms and swarms of flies, and they're all going to be the same, right? So another way to maybe another analogy to think about would be like this: the class is a genetic code, and from that genetic code, right, which describes how the fly flies, bites, rubs hands, poops, and so on, and has properties of age, sex type, and so on, right, I can birth as many individual flies as possible. And so genetic code is called class, right, and each one individual fly is called object in that paradigm, right? Or you can think of it, instead of genetic code, you can think of it as blueprint, right? So if you want to make a car, for example, you need a blueprint, you need drawings, you need like engineering drawings, right? Specifications and so on and so forth. So I can have like a bunch of these blueprints that describe this car, right? Like this is how the engine is going to be built. This is how many wheels it's going to have. This is its top speed. This is its number of seats and so on and so forth, right? Body type, everything, right? And then from that blueprint, which is a class, I can start stomping on a conveyor belt individual cars, right? One after another. And maybe certain properties will change from car to car. Like it honestly doesn't matter if the car is red, blue, or green, right? It's a property that can easily change with every individual car without affecting the blueprint. All I'm going to have to say in the blueprint is that the body of the car is going to be painted a color. It doesn't matter what color it's going to be. It's just going to be painted something. And when I create every individual car, I can say, well, this one's red, this one's green, this one's blue, and so on. Okay. So, yeah. So that way, all of these collections of values can be represented as a single entity, and we can start operating them in code as a single entity. Okay, so this is kind of like a hint back to our previous conversation. Wouldn't it be nice if instead of keeping track of God knows how many arrays, right, we could keep track of entities, I'm sorry, we could keep track of these, like, yeah, whole entities that would contain those values and would both have properties and methods. Okay. So, um, uh, our bowl, right, like our little circle, bouncing circle, can be an entity like this, right? And it will have certain characteristics, right? Here they are, these characteristics, and it will have certain actions. It will have certain the ability to do certain things. So it will have methods, properties, and methods, right? And so again, in order for us to create this, we need to first build a blueprint, build a class, and from that class start implementing those entities. Okay, so let's see how we can do this. Um, so one um, a common way of doing this is to create a separate file for all of your classes, right? Just to compartmentalize things, right? There's nothing wrong with adding the blueprint at the end of the existing sketch, but it's sort of a convention because it kind of helps you, like, oh, here's the entire written blueprint. I've figured it out. I set this up. And then from there, I'm just gonna start stomping cars, right? Or like, I don't need to think about the DNA code every time I'm dissecting a fly or creating a new fly if I'm like this weird, crazy Frankenstein type genetic engineer, right? I don't need to think about every particularity of its DNA code. All I have to do is zap the corpse with electricity, and I get another live fly, right? All right, without getting too macabre, let's create a new file, right? So like in our sidebar, I'm gonna go over here and create a new file. And so my little bouncing ball, I'm gonna call it a particle, for lack of a better word, right? Like particle sounds as good as anything else. So let's add a file called particle.js. Okay, so it's empty. One important thing, please don't forget this. If you're creating a new file and you want that file to be incorporated, please make sure you add this to your index.html just the way your sketch is added to index.html, right? So otherwise, your page is not gonna know where to grab this code from. So let's go and add it exactly the same way. So script source equals, and that's going to be particle.js. Okay, and so we're going to close the script. Okay, and so now it should be in our system. Great. So let's go to sketch.js and let's see what are some of the values that we want to potentially reuse in our particle, right? So it's going to be the positions, the velocity, the radius, right? We might want to reuse the color, right? And then we might want to use some other properties, right? But these values at the top, they seem to be relevant, okay? So let's grab those. And let's go to particle.js. I just cut them out, and right now they're just in the buffer of my computer. I'm gonna paste them in 1 second, but for now, let's create the overall structure. Okay, so it's gonna be a class, so let's declare it as such. Class particle. Okay, and then when you declare a class, all you have to do is just put in the curly brackets. That's it. Okay, and so the first method, right, the first action that any class will possess, every class will possess, is the ability to instantiate itself, right? So since it's a blueprint, we should be able to make something from that blueprint. And one way to do it is to engage its constructor. So constructor is the method that creates an object from that class, right? Creates a thing from the blueprint. So a constructor is a function, right? It's a method. We write it like this. And constructor, I want to make sure I didn't make any spelling errors. And in the constructor, when you create a thing, the very first thing that you probably want to do is set up its properties, right? Is our car going to be red or is it going to be blue? is our amphibian going to be male or female, right? So let's add those properties here, right? So it's going to have position x, position y, velocity x, velocity y. But one important thing, and that's kind of like a peculiarity of JavaScript a little bit, is when you're creating those, right, you're going to say that these are going to be the properties that belong to this particular particle. So instead of saying let position x, you say this dot position x, okay? And similarly, I'm going to copy this, and like it's going to be this dot position y, this dot position velocity x, this dot velocity y, this dot radius, and so on and so forth, right? And then we can also say like this dot col for color, right? Something like that. And then we expected an assignment or a function call instead of so an expression. So just basically like, I expected you to give me a value, but instead it seems like you're just trying to use it. Where's the value? So let's make the value, right? So it's we originally started making values here, right? And so instead of this push, it was supposed to be like this, right? So what we can do is take these values, right, cut them out, and paste them in here, right? So position x was width times 0.5. Okay, and I think that it's going to be faster to just type instead of click through. Times 0.5, click through the file. So I'm going to do the same thing with velocity, random between -4 and 4. And I'm going to show you a much faster way of doing this in a little bit, but just like with the object-oriented programming, I want to show you the problematic way of doing this and then how the solution could be provided. So radius was 50 and color. Let's use the same color. Just want to grab that color. So 50 and the color is going to be color with these values. Okay. You can randomize the values too if you wish. But okay, so we have a constructor with the properties. Okay, so then we can say, all right, so what are the things that our particle will be able to do? What are going to be its methods, right? So one thing that we're noticing is that it's going to be able to move. That's a logical thing, right? So let's move it around. And so in here, we said that the movement consists of the adjustment of the position, right? So let's take that. And then if you're going to be doing this a lot, you're going to notice this one weird little thing, right? So let's say move, right? So let's call this move, and let's paste our values in here. So move is going to be the method, and then these values that we just copied and pasted are going to be the actions that comprise that method, right? So one thing that you will notice, like I said, is that if you're copying and pasting, they're coming in without this weird this dot thing, right? And so this dot becomes really important. So please don't forget to add it before every value that pertains to a particular class. It's kind of annoying, but that's how JavaScript wants it. And some other programming languages don't insist on it. They make certain assumptions. But in JavaScript, when you're creating your classes, you'll have to do this, right? All right, so we have movement, which consists of adding velocity to the position. And then we also have the bouncing part, right? And this is where you can start getting like basically start to figuring out how do you want to express your system. Maybe bouncing is going to be a different method altogether, right? Sometimes it bounces, sometimes it doesn't bounce, right? I don't see a scenario when my particle shouldn't bounce off of the edges, so I'm going to make it a part of movement. So I'm going to take all of this and I'm going to paste this into the particle as a part of its movement function, right? Movement method to be precise, right? So a function that belongs to a class is called a method. Terminology, right? So again, all of those values came in without the this dot. And so we have to go in and paste this, right? So again, for all the values that pertain to this class. So it's this dot position y, this dot radius, this dot velocity y, and so on and so forth. So all right, so we have the movement, and then we have another important function that this particle can perform, right? Another action that it can perform, also known as its method. I'm sorry, I'm just like dropping terminology on you, but another method that we need to perform is the display, right? We need to show this particle. It needs to show up on the page, right? So we're gonna take this, which is to me is the display of this function. So let's say display, right? And we're gonna say the display is gonna set up a fill and it's gonna draw the circle. And it's gonna set up the fill with this color, right? So like whatever color we set up in the particle, because maybe we want to randomize it, maybe we want to make it different or something. We're just going to use whatever is the color of this particle. That's what the fill is going to be. And then it's position X. What did I do? Oh, nope. Copy, and then position X, position Y, and its radius. All right, so we have a particle that can create itself, it can move, and it can display. So let's see how we can use it to our advantage, right? So let's simplify this significantly. We're going to be creating a few of them, so let's create an array of particles, and we'll call it particles, right? And it's going to be an array, okay? And so we can say particles dot push, so add to the array at the end of it. And what do we need? We need a new particle. Okay, so if you wanted to add a new object from a class, this is how you do it. You literally create a new particle, and this specific code, right? This type of code invokes the constructor of the particle, right? So it will automatically say, oh, class particle. It will be the constructor function that I will be using in order to create this new particle. So what that tells you is that every class has to have a constructor method, right? Move, display, whether they're there or not, doesn't matter, but every class has to have a constructor, okay? All right, so we create a new particle, right? And then we can say that particles dot, and if you remember, we looked at for loops, right? Probably by now a fairly common loop that you have started to work with. So when we say for, starting with like a certain index, let's say in index number 0, for I equals 0, as long as I is less than the length of the array, I plus plus, and then do something, right? So there is a shorthand for this. I might have shown this to you, but it doesn't hurt to kind of go over it again. For each. For each means that I'm not going to bother writing I equals 0, I plus plus, and whatever. I'm always going to do it for every single particle in the array for as long as we have particles in that array. So I can just do it as a shorthand for each, like this. And then I can say something like that, right? So I'm going to say basically for each particle represented as a value p, right? I'm gonna look at an array of particles. This is particle 0. Now you are gonna be p. For the next loop, now you are gonna be p. For the next one, you are gonna be p, right? So for each particle as p, right, I am going to do something. This is a fet or arrow syntax for a function. So I'm saying like perform this function, p dot move. So particle invoke its move method, right? Move yourself, and p dot display. So move yourself and then show up, right, on the screen. And that's pretty much it, right? So that's really all I need to say. So let's see if it works. I don't know, maybe there's some errors, but we can try this out. All right, it seems that we got it. Okay. So far there are no real advantages, right? Like, yes, our code is shorter in the sketch, but it's definitely longer in the particle. But we can start adding more and more particles, right? And we don't have to worry about uh, arrays and keeping track of separate values. So for example, one thing that I can do, a very common thing, is add a mouse release function, right? So those are there are certain things that you can perform with your mouse and with your keyboard, right? So like, let's put a search, mouse. Okay, so mouse click, drag, move, press, release, mouse wheel movement, and so on and so forth. So like I'm going to be using mouse release functionality, and then you can find out furthermore like things you can do with the keyboard, things you can do with the mouse, and so on and so forth. So we can say like with the mouse, we can track when a mouse button is released. So I press the mouse button and then I release it. Okay, so that constitute the full click, right? So instead of calling it a function that once after mouse button is pressed and released, I like to do mouse release, right? So that means that I have to press the button and I have to release it afterwards. Force of habit, there are certain performance advantages to it. I think mouse clicked works just as well, but I don't know, nature of habit. I prefer mouse released, right? So function mouse released. Okay, so after the mouse button has been released from the press, so here's what I'm gonna do. I'm gonna push another particle into an array of particles. So particles dot push new particle. Okay, all right. So let's see if it works. I got another one, and I got another one, and they're all the same. But this is where, except for their velocities are different, right? Because we randomize their velocities. So some of them are moving one way, or others are moving another way, right? So we could potentially randomize their color, right? Right. Let's say like the first value random of 255. Okay. And we can randomize the radius random, and that's going to be between, let's say, 20 and 60. Okay, so I can try and running it like this. So now we have slightly different sizes, all have different amounts of red in them, right? So some are grayish, brownish, some are reddish, some are bluish, greenish, whatever. So, but they all have different colors and they all have different velocities, so they all move differently. So when I create them, I just randomize certain values. But, and this is where we're going to keep moving, like pushing things next step and next step and next step. So wouldn't it be nice, right? So like this is where I'm like pushing the advantages of the object-oriented paradigm. Wouldn't it be nice to create a new particle wherever I click a mouse? So right now they all start in the middle, right? And I can randomize it, right? But it's still not going to be at the place where the mouse is clicked. So if you remember when we talked about our pond model, we said that like particles can exchange, or like objects can exchange information, right? And so that what that means is that they can exchange information with a lot of things, even with outside objects. And so here is the thing: a mouse is an object in the system. And so for like pretty much everything is written in object-oriented paradigm now. But a mouse, you can consider it an object in the system, right? And so if you look at the reference at the mouse uh, description, you will see that there is a mouse X value, right? It's a number that tracks the mouse's horizontal position, and it's we have mouse Y. It's a variable that tracks mouse's vertical position, right? So we have the ability to take the mouse's vertical and horizontal position, and if only there was a way for us to pass this information into the constructor, so when the new particle is created, it is created in that specific location, right? We'd be golden. Well, obviously there is, otherwise I wouldn't be talking about this. And so the way you would do it, you would pass this information literally into the constructor. So let's say whenever I'm creating my particle, I would say I would give it a value of X, right? And a value of Y, okay? And so I always add these underscores into the values that are passed into constructors or into functions in order to let me know which ones are passed in. So our position X is going to be set from the value underscore X, and our position Y is going to be set from the value underscore Y, right? So if I stop this and if I try to run my sketch this way with this code, I'm actually going to get an error, right? So here it is. So it says that a particle was expecting a number for the first parameter, but received a not a number. Nan stands for not a number. It received a not a number instead. It received a nothing. Nothing is not a number, and therefore it errored out. Okay. So what that means is that when we're constructing a particle, we actually have to give it a number, right? So, and maybe when we're building the very first one, we can give it the width times 0.5 for the X, and the width or height, sorry, height times 0.5 for the height. And we saw this, right, when we were making functions, right? Like you can create a function and you can pass values into it as arguments, right? And then you can start using those functions with the with those arguments. And so the same idea with the constructor for a particle or for any other class, right? And so, okay, so we're going to create a new one at the center in the very beginning, just so that we have something. And then once the mouse is released, we're actually going to track the mouse X, mouse X, and mouse Y positions, right? And we're going to pass those values in. Okay, so now I have a particle that's created wherever I click my mouse. Okay, so here's an interesting challenge if you want to try and save it yourself. I'm not going to give you a solution here, but like, what if I click my mouse very close to the edge? And see how the circle gets stuck in there? So here's an interesting question for you. Why does it get stuck? And how can we make sure it doesn't get stuck? Right? And as a hint, it has to do with the way it bounces, right? And think about a way to like not get it stuck. I'm not going to give you a solution. Sorry. I just, there are a lot of other things to talk about, but think about how to not make it stuck. If you want, post your solutions in the comments to the video, right? That would be fun. Maybe at some point I'll make a video showing you how to get it unstuck, but that's a challenge. All right, so I want to move on to another component, right? So we said that particles, like objects, can exchange data, right? And we can actually visualize this ability, and I think it would be very interesting to visualize this ability, right? And so what I'm going to do, I'm going to create a property for my particles called friendliness, okay? And then my particles will have the ability to connect to other particles that are in the certain vicinity. And the more friendly a particle is, the further out it's going to reach in order to create those connections. Okay? So let's see how we make it, how we can make it happen. Right, so I'm gonna say this dot friendliness, right? Friendliness is equal to, and it's gonna be a random number, and basically it's gonna be a how far away I'm going to reach to keep trying to connect to another particle, or to keep connecting to it, right? I'm gonna say it's gonna be a random value between, let's say, 70 pixels and 250 pixels. Okay, so in order to make those connections, I'm gonna give it a method, and let's say like we have move, display, and then let's say reach out, right? Let's reach out to other particles, right? And so in order for me to reach out to other particles, I need to know about those other particles. So what I'm gonna do, I'm literally gonna pass in an array of all the other particles in here. Okay, all particles, right? So this is going to be an array of all the particles in my system. And so I'm going to say all particles, sorry, dot for each, right? So we're going to use that for each function again. So when one particle is trying to reach out to all the other particles, it's going to go through the entire array, and it's going to try and reach to every one of them depending on how far away it is from them, right? So I'm going to say, right, we already saw the format, other p, right? We're going to call it other p. Okay, so, and first we need to make sure that like at some point in this array, it's going to find itself, right? So we're going to say if, well, actually, let's not. But it's gonna connect to itself always, right? It's gonna be another one of those things that you can save for. You can kind of check for it. Like one way to check for it and see if you can figure out how to write this out is like if the position of this particle and the position of this other particle is exactly the same position, then don't do anything, right? Um, but if this dot position position x, right? So if this dot position x is within, like, so basically this is where you're gonna have to start kind of measuring the distance, and let's go look in the reference if we can measure this distance. So let's do search distance. Is there anything for distance? There isn't anything for distance because it's called dist. Okay, so we have dist, right? And this is a function that can calculate the distance between 2 points, right? The version of dist with 4 parameters calculate distance in 2 dimensions. The version of distance with 6 parameters calculates distance in 3 dimensions, right? So we need to give an x1 and y1, an x2 and y2, right? So we're gonna say basically, right? And so you can just look at the example. So we'll start with distance, right? Distance, and we'll say this dot position x, this dot position y, right? And then so we need x1 and y1, which is the position of this particle, and then other p, and let's make sure we spell correctly, other p dot position x. Every particle has a property dot position x, right? And other p dot position y, and it's getting lengthy, and there's a way to deal with it better, right? Like I keep dropping hints like, oh, there's a better way, there's a better way. I'll show you this better way right after we write this friendliness and reaching out components. I'll show you another better way, right? So we are measuring the distance between the center of one circle and the center of the other circle for every single circle in the system, right? And if this distance is less than the friendliness of this particular circle, right? So like this dot friendliness, right? Is that how I spelled it? I don't trust myself. I'm just going to copy and paste it to avoid unnecessary errors, right? So if it's less or the same as the friendliness factor for this particular circle, right, we are going to draw a line. Let's set the stroke to be, let's say, 0, 0, 1. Okay, and let's just set the stroke to be 0, right? And then we are gonna set the line. And the line literally is just going to be this, right? We can say like, we can take this position, this position X, this dot position Y, the other P dot position X, other P dot position Y. And that's how the line is going to get drawn. So we can copy this and draw the line like that. Okay. It's lengthy and kind of cumbersome, but let's see if it works. Oh yes, it doesn't work for one very simple reason. We told them how to reach out, but we never told them to reach out, right? So we basically need to say that p dot reach out. So you move, you display, and then you reach out to all the particles. So let's put the particles array in here. Right, so let's stop this, run it. So you see this dot in the center, it's basically reaching out to itself. All right, cool. So we have these neat little lines that are forming and the particles are reaching out to each other. Time to refactor. So there is a much better way of writing this, right? So first of all, let's set up our colors properly. Let's switch to our color mode. Let's switch our color mode to HSB, right? And it's going to be our 2 pi 1 and 1. Okay, so that just makes things a lot easier to work with in color, right? And then our background is just going to be 0, right? Time to refactor. Yes. So particles, for each particle, that all looks good and fine, and all this all looks good and fine. Let's go and change the way our particle is written a little bit. So first of all, we can change all the color values, right? So I'm gonna set the color to do this one interesting thing. So we already looked at a mapping function, right? And so I'm going to say, depending on where the particle is created, it's going to take that color, okay? So remember, the mapping function maps one range to another range, right? So just again, to give you an illustration, right? So let's say that we have a range between, in our case, we have our sketch, right? So we have 0 here, and we have full width over here, okay? In our case, it's going to be 800, but it almost doesn't matter what that is. And then we have our color system, right? And I want the hue of the particle to be red over here. Remember the color wheel, right? So it always starts here, and then it goes red, and then somewhere here it's going to be like orange, and then it's going to be like yellow and green and cyan and like blue and like purple and fuchsia and scarlet and so on and so forth, right back to red. So our red is here. So I need to take this whole range from 0, and in our system we set up the range to be 2 pi, right? Because that's radians, and that's how we operate. So we always want radians. So this is the red is going to be 0 radians. 1 pi radians is going to be cyan, right? Half a pi of radians is going to be like this orange yellow. Let's call it yellow. And so on and so forth, right? So I want to make sure that this cyan is sitting somewhere in the middle. Red is here, and then over here we're back to here, so that yellow is somewhere here, and then blue, and then purple, and then fuchsia and scarlet, and so on and so forth, right? Just like we have blue over here, and then purple over here, and then fuchsia over here. So I'm taking this range from start to finish, and I'm remapping it to this range, right? Another way of looking at something like this would be to say, like, all right, so we have a range, right? Let's say this is the range between 0 and 2 pi, right? And then we have another range, and then it's a much greater range between 0 and 800, right? That's the range that represents the width of my sketch, right? So I want to relate the 2 pi to be here. I want my 0 to be here. I want my 1 pi to be equal to 400, right? So when I get a value in this range, let's say it's a value that's pi, I want to remap it to another range and get a 400. And then if I get the value here, which is 2 pi and a half, I want to remap it and get the value of 600. And so on, all the values in between, right? So I'm taking one range and remapping it to another range. Okay, so let's do that. So I'm going to go into my particle. I'm going to say the hue of my color, right, is going to be the result of a mapping function. So I'm going to take that value of x that I've passed on, right, so underscore x. So it's going to be on one side to the other side. I'm going to say the x is going to come as a range between 0 and width. So it can be 0, it can be 20, it can be 40, it can be 400, it can be up to 800 because that's my width, right? And then I want it to then be remapped to the range between 0 and 2 pi because that's how my colors are set up. So for full clarity, it's going to be like this relationship is going to be more like backwards. I'm going to get an 800 and I'm going to make it into 2 pi. But the most important thing is that there's going to be like a direct correspondence between these values. Okay, so all right, so I have a map that takes the position of my circle and then gives me the hue of the color. And then let's do 0.9 and like 0.9. Okay, so that's going to be this this one thing that we can do. So let's, and then, oh, okay, so the stroke, right, we're going to make it 0 and 0 and 1. So I'm going to make them white simply because the background in my sketch is now black, right? I made it 0. So the lines between the circles are going to be white. Okay, so it's red but no saturation at all, and so it's all brightness, so it's just going to be fully white. Okay, and then yeah, so let's see how that works out. Maybe one other thing I'm gonna do. I don't want like these bright white circles around my particles, so I'm gonna say no stroke. So let's run this. All right, let's add some friends. So depending on where I click, so if I click here, I'm gonna produce a red one. It's ochre, but whatever. If I'm gonna click right here, it's gonna be like a bluish cyanish, right? If I'm gonna click right here, it's gonna be probably yellow greenish. There you go. Here it's gonna be closer to blue, actually actual blue, right? So red over here, red over here, cyan, blue over here, green, yellow, and so on. So there is a certain predictability, right? When you have a lot of these circles, they start getting very friendly. So there are a lot of lines. Um, so yeah, that's great. Another thing that we can do, we can actually reduce the number of um, variables in my particles. So the class and object system, object-oriented programming, is so intrinsic to all programming paradigms by now that you have a whole bunch of classes that are pre-written for you. Okay, let's give it a couple of friends. So they're pre-written for you, and then what that means is that you can use those useful classes um, in your own system, and they're like helpers. So one of those helpers is called a vector. So a vector is is something that consists of two values, for lack of a better word, right? So let's unpack a vector a little bit, right? So let's go back here. So and why not just take everything, delete it, and start our conversation about vectors. So if you remember middle school math, or whatever kind of school math, right? You remember maybe that a vector is something like an arrow, right? Right? Something like this. So an arrow has a direction and it has a magnitude. Okay. So actually, let me draw a slightly different arrow. I'm gonna erase this one, and I'm gonna draw an arrow, and you will see why I'm drawing a slightly different arrow. I'm gonna draw an arrow from here, and I'm gonna draw it all the way to here. Okay. So this arrow has a direction and a magnitude, right? And we've represented vectors like this, right? That's a vector that it has two values that you should be able. So it points in some direction, right? And it has a length. That's what the magnitude means, right? And so we can store these values, right? Like where it points and what the direction is, but you can actually easily and quickly derive those values. And so let's see how, like, there is like a simpler way to store values and then derive the direction and magnitude from those. So I'm gonna draw two more lines here. This one, and let's do a different color, maybe like this one. Okay, and we get a triangle. Okay, so one thing that you might immediately start thinking of is like, oh, wait a second, we just spoke about trigonometry, and it really reminds me of trigonometry. And you can think about it this way. Sure, you can say that this is a hypotenuse, this is an adjacent, and this is the opposite. Okay, great. And but another way of thinking about this takes us back even further, and that is to start thinking about right angle triangles. And if you remember Pythagorean theorem, right, we can easily get the length of this, right, if we use a Pythagorean theorem, right? So the length of the hypotenuse is hypotenuse squared is equal to a squared times opposite squared, right? So what that means is that hypotenuse is equal to square root of a times o squared, right? So let's see. And the reason why I drew it like this is because a right now, if you notice, is 4 values. So it's 4 squared times 3 squared, right? So we have 16. Sorry, not times. What am I saying? Plus. It's a plus right here, right? It's a plus. So 4 squared plus 3 squared, it's 16 plus 9. That's 25, right? And the square root of 25 is 5. Right? So we have, if our A is 4 and our O is 3, our H is 5. Okay, so my bad. Sorry about this. It's again, just to reiterate, this is hypotenuse squared is adjacent squared plus, not times. That would be kind of crazy. Um, but yeah, so we have this relationship. So what that means is if we store the values of a and if we store the values of o, we can easily derive the value of h. And the reason why we would want to do that, maybe store it as its adjacent and opposite component, is because it actually maps very neatly to our coordinate system, right? Because we have x on this axis and we have y on this axis. And so we can store the x component of the vector and we can store the y component of the vector, right? Um, and so we'll come back to the vectors in a little bit, but once we have those components, we can start like quickly and easily performing operations on vectors. Okay, so going back, let's look at this distance function, right? So like, and it says, hey, use p5 vector dot dist to calculate the distance between two p5 dot vector objects. All right, so we have objects called p5 dot vectors, and it seems that like they're almost suggesting, hey, if you want to do this like distance operations, maybe you should use vectors, right? And use this distance function on a vector. So let's look at what vectors look like in P5. And so it's a class that describes a 2 or 3-dimensional vectors. And in our case, 2-dimensional vectors means that the vector has the x and y component, and 3-dimensional means it would also have like a z component. And so instead of just being drawn in 2 dimensions, it would be drawn in 3, right? So a vector can be thought of in different ways. In one view, vector is like an arrow pointing in space, and vectors have both magnitude and direction. But vector objects are often used to program motion because they simplify the math, right? Um, for example, moving the ball has a position and velocity. Hint, hint. Now you're figuring out why we were drawing the particle in the first place. And position describes where the ball is in space. And the position vectors extends from the origin to the ball's center, right? So if we wanted to store a position of the ball, we can also do this as a vector in order to simplify the math. And the origin would refer to, in this case, a 0, 0 point, right? And then maybe if our ball is right here, we can say, hey, this is the x component and this is the y component, and this would give us the position of the ball, right? It would be the vector from the origin. Okay, and then the ball's velocity can be the position, the ball's speed and the direction of the movement. If the ball is moving straight up, the velocity vector would point straight up. And if we need to add the ball's velocity to the position, you can just say position dot add velocity. And so remember, vector is an object, right? And so it's a very abstract mathematical object, but it can still perform certain action. It can still do methods. And so one of the methods that you can do is just say, hey, add a vector to this vector, right? Add a vector to me. I want to add another vector to myself, and that would work like this, right? So you can use the create vector function to make an instance of this class, to make an object, right, from the class vector. So if you wanted to use vectors, and vectors simplify the math significantly and simplify the code significantly, here's how we do it. In our particle, instead of having a position x and a position y, we would have just position. And that position would be a vector with the x and y components that are coming from these mouse x and mouse y values that we're passing into the constructor. And if you wanted to have a velocity x and velocity y, you would just have one velocity and it would be a vector that would again have two components, but in this case, the two components would be just simply random, right? So I'm gonna generate one random value, and then I'm gonna say comma another random value, right? And so, okay, so that's great. Then if you wanted to access those, right? Well, so first of all, let's just make this very simple. We can say this dot position dot add this dot velocity, right? So instead of having two lines, we just make it one line. And then if you wanted to access individual components, right, the x component to the position or the y component of the position, you keep using this dot notation that just simply means access a property or a method inside a class or inside an object if it's instantiated, right? So we can say position dot x instead of position x, or we can say, well, radius stays radius, right? And then here also position dot x instead of position x, and same for the velocity, right? Velocity dot x. And all we have to do is just add this, and I'm kind of like spacing it out, add this like one dot, and we will get access to the components, right? And then same with velocity dot y. Okay, same deal. Position dot x, position dot x, right? So it simplifies the code quite a bit. We only need to have one object for position, one object for velocity, and then if we can use them for a certain operation, that's great. We simplify the code even further. And if we still need to access those values individually, well, we're not really we're not adding any more complexity. All we have to do is just say position dot x instead of like one value, position x, right? So that actually makes things a lot simpler. Plus, there is this very helpful distance function that will allow us to rewrite our distance checking, right? And make this this distance checking a lot simpler, right? We can just simply say over here, right? This dot position dot distance to other p dot position. A lot shorter, right? So take me and take and measure the distance to the other position, right? From myself, this dot position, and then this position has a distance method, and then we can do that, right? So it's still particle GS expected a number for the fourth parameter. Interesting. Line 33. Oh, yes. We forgot to do these guys. Position.x. How forgiving this is. Position.y. And then other p would do the same thing. Position.x and position.y. Okay. Yay. All right. So let's see, how is this position x, this position y? Okay. All right, sorry if you noticed there was like a little glitch here, right? So there's this dot and like there's some like lines and dots just floating around in space, and they're all being weird, and it's because I made a mistake when I was refactoring the code, and it happens often, right? It's a mistake. It still works because nothing violates anything, right? Like I'm not doing anything that I'm not supposed to do, but it still doesn't do what I want it to do, right? So it's not an error per se, but it's definitely a bug in the system. So I had to look a little bit into like where the bug is coming from, and of course it's from a spelling mistake, right? So when I'm drawing a circle, I'm saying this dot position x for the x value and this dot position x again for the y value. So I have to change this to the y value, and now it's all fixed and everything is back to normal, right? So so yeah, that's fantastic. Again, if you haven't figured it out yet, let's try and quickly fix the little dot in the center that each and every one of them has. Again, that's coming from the fact that they're not checking for themselves in the array, right? So we can say that if the position to the other p is less than friendliness, right? But we need to add another factor. If this, let's say this dot position is not the same, right, as other p dot position, and, right, so we need to have two conditions, and double ampersand will give you an and. So it can't be the same, right? So let's run this. And now it stops reaching out to itself, right? So if it's the same, then we're not drawing that weird little dot in the center, right? Because obviously, like, if it's the same, it would be less than the friendliness. It would be 0, the distance between itself and itself. And so there you go. That's a quick and easy way for you to check something like that. All right. So this is like a quick introduction to what object-oriented programming do for you, and at the same time we talked a little bit about mapping, talked a little bit about vectors, and we're going to come back to this idea in the next video. It's going to be, again, just expanding on what object-oriented programming is and how it works. So yeah, I'll see you then. Bye.